Okay, so in this video we're going to be talking about buffers and what a buffer is. So the first definition we're going to get to is, what is a buffer? Buffer is a solution that resists changes in pH when a strong acid or base is added. So, a good example is your body's blood. Your body's blood has a specific buffer that controls the pH of your blood. Now, the pH of your blood has to be within a specific range. If it goes out of this range, you will develop health problems, and these health problems could potentially kill you or put you in hospital. So, the pH range depends on the book that you or resource you use. It ranges between 6.8 to 7.4. And it's consisted of the bicarbonate carbonate buffer. And so we talked about pKa's and Ka's earlier in the acid-base topics, and so this all boils down to what the Ka values are for the acid and the Kb values are for the conjugate base. And so this is going to be based off a ratio of the acid and its conjugate base, essentially. And we're going to see that as we go through the different examples and we discuss, various buffer solutions. Now, going back to what the definition of a buffer is, buffer is something that resists changes in pH. And that's when you add in a strong acid or a base. Now, if you have just water sitting there and you put a lemon juice in it, well, of course, the water is going to turn acidic because it's going to be relating back to whatever acid or base is put in. In that case, the lemon juice would be acidic, so itself becomes acidic. Now, if you were to take a buffer such as the bicarbonate and carbonate buffer, and you're to put in hydrochloric acid, or even the lemon juice for that matter, it shouldn't change pH very much, because if it's a true buffer, it's going to resist that change. Now, once you get out of this buffer, a buffer zone is what we're going to call it later, you're going to start to see the pH be affected more drastically. But as long as you're in that buffer zone, and that buffer zone is always going to consist of the acid and the conjugate base, it's going to be considered a buffer. Anything else is something different. So throughout a buffer's life, it should not consume itself or be affected greatly by the addition of a strong acid or base. A buffer is composed of both acid base and conjugate base acids. So we're going to look at a solution where we have benzoic acid and sodium benzoate. And so one of the things we're going to talk about is how we set this up in relation to the ice chart that we've been using with equilibrium type problems. And so here we have benzoic acid breaking down to form benzoate and hydrogen ions. And the concentrations of this are given to you as 0.4 molar for benzoic acid and 0.2 molar for sodium benzoate. Now, the sodium itself is a spectator ion, and so when you put that in solution, sodium ions are not going to be involved in the reaction at all. It's actually the benzoate ion, because it's the conjugate base of benzoic acid. And so you'll set up your ice chart, and so we have 0.4 molar for the benzoic acid, and then we have 0.2 molar for the sodium benzoate, and the hydrogen ions are 0 to begin with. So the change is going to be minus X for the reactant. It's going to be plus X for both of the products here. So we'll plug in this equilibrium here, and you'll notice this is very similar to a problem that was worked in the common ion video. And so we have to look at the Ka value for benzoic acid. Benzoic acid is 6.5 times 10 to the negative 5. And we set that equal to the concentration of benzoate times concentration of H plus divided by the concentration of C6H5CO2H. So now we input the values from the equilibrium. In here we're going to solve for x. So we're going to make that assumption that the minus x and plus x are negligible, so that way it helps to kind of simplify the math. And again, if you can use the quadratic equation if you want, but I'm going to try to keep it as simple as we possibly can for now. So what you'll notice here is you'll see this ratio here, or you see this pair where you have the conjugate base over the acid. And whenever you see this pair show up, usually you're going to be knowing you're working with a buffer. So what we need to do now is we need to plug it in, and we need to solve for the value for x. So x is going to be equal to 6.5 times 10 to the negative 5 multiplied by 0.4. Then we're going to divide that by 0.2, and then we need to solve for x. So 6.5 times 10 to the negative 5 times 0.4 divided by 0.2 gives us a value of x equals to 1.3 times 10 to the negative 4. So just like before, we need to figure out the 5% rule, and we're going to take 5% of 0.4. So 5 times 0.4, that gives me 0.02. So this x is fine. So our pH for this solution will be equal to negative log of 1.3 times 10 to the negative 4. That gives me 3.89 for the pH of this buffered solution. So just a little simple recap here. This ratio that we're talking about, this ratio is an important ratio. This ratio is the ratio of conjugate base over acid, and as long as you have that ratio present, you're going to have a buffered solution. Now, this ratio was studied by Henderson Hasselbalch, and so their names are Henderson, Hasselbalch. So these are two scientists that studied this ratio, and then there's a derivation that goes through solving for this ratio and how to solve for the pH of a buffered solution. But I'm just going to get right to the point here. And this point is pH is equal to pKa plus the log of the conjugate base. We're going to call this A minus, just for future note, divided by the acid. In this case, we're going to call this HA. And so as long as you have this ratio, as we were talking about earlier, you're going to have a buffered solution. Now, what is pKa? pKa is very similar to pH, where you take the negative log of your Ka value. So one thing you're going to always want to make sure to do is know your Ka. If you don't know your Ka, but you know your Kb, you can actually solve for Ka from Kb. And you can use the equation pKw is equal to Ka times Kb. I guess I should say Kw. Let's do that. Say Kw is equal to Ka times Kb, where Kw is the water constant, 1 times 10 to the negative 14. So, a couple key equations here that you have to know. All right, you need to know Henderson-Hasselbalch equation, and this equation here is how you go from Ka to Kb and vice versa. Last comment here, this ratio is an important ratio. Remember, as long as you have the conjugate in the acid or the conjugate in the base, depending on the type of equilibrium you're working with, you're going to have a buffered solution. And what's a buffer do? A buffer resists changes in the pH of a solution. Okay, so in this particular problem set, we're going to be working with a buffered solution. And in this particular example, we have a solution that's composed of 0.5 molar acetic acid and 0.2 molar sodium acetate. Determine the pH of the solution initially. So we're going to set up the equilibrium. We're going to write in the ice chart, and then we're going to go through the expression and solve for X, which will get our pH determined initially. So let's go ahead and get started here. Acetic acid is CH3, CO2H. It's going to be breaking down to form CH3, CO2 minus plus H plus. In the ice chart here, we will have 0.5 molar acetic acid and then 0.2 molar acetate. This is going to go down. 0.5 minus X. This will go up. And then this is 0, just like we've done. Alright, so Ka is equal to the concentration of acetate times concentration of hydrogen ion divided by the acetic acid. Alright, this is equal to the Ka value, which is 1.8 times 10 to the negative 5. So acetate is 0.2 molar. We're going to not worry about minus X and plus X at the moment. We'll use 5% rule, and we will determine X using the simplified way here. So go ahead and solve for X using the calculators. I get my X to be equal to 4.5 times 10 to the negative 5. And so 5% of 0.5 is 0.025. So 5% rule. So we get 0.025. That's 5% of 0.5. That's valid. So we can solve for the pH of the solution because X is equal to the concentration of hydrogen ions. So pH is equal to negative log of 4.5 times 10 to the negative 5. And plugging that in, we end up getting 4.35 for our initial pH. So this is initial pH of the solution. Now, in our next problem, the same solution that was then titrated with 10 milliliters of HCl. Now, this is where we have a different problem taking place. So the HCl is added into this solution that contains, I'm going to draw a little beaker here for us to look at. So we have this solution. In this solution you have acid, and then you have your acetate ion. Let's see here. Let me make this a little bit neater. CH3, CO2 minus. So we're going to add in HCl. Well, HCl breaks down to H plus and Cl minus ions. This H plus is going to react with the acetate ion. The question is, how much of the HCl is going to react with the acetate ion? That's what we have to do. So this is a two-part problem. The first part is applying some stoichiometry, and then the second part will be using the ice chart as we've been doing above. Now, one thing that I want to make a note is that if you're working with a buffer, you also can use the Henderson-Hasselbalch equation, and I could have used that in the initial problem, but we just went ahead and just solved for using the ice chart like normal. So whichever way is comfortable for you, that's what way I want you to do it. So first part, stoichiometry. All right, so during the stoichiometry part, we're going to calculate before and then after. And you say, well, what do you mean before? Then we're going to figure out the moles of compound before and then afterwards. So in this particular problem, the HCl is going to react with the acetate ion, and it's going to form acetic acid plus some conjugate, which it's not important. In that case, it would be sodium chloride, so that doesn't matter. Now the question is, how much do we have before? So what we do is, you can convert your milliliters into liters, but that's not necessary. And I did not give any specific volume of what we had in the first problem up here. So let's say that we have, I don't know, let's say we have 10 milliliters of the 0.2 molar sodium acetate. So we're going to take the 10 times 0.2. So we're going to take 10 mils times 0.2 molar, and that gives me 2 millimoles. So that you don't, whenever you don't convert it into liters, and you do milliliters times molar, that gives you just millimoles. And so we're going to do the same thing with the HCl. So 10 times 0.1 gives me 1 millimole. Remember, this here is 10 times 0.1. Where did the 10 come from? The 10 and the 0.1 come from up here. So now we also need to figure out how much of the acetic acid we have, and we're just going to keep 10 milliliters of it. We're just going to keep it consistent with the sodium acetate. So we have 10 mils of the 0.5 molar. So we're going to take 10 mils times 0.5. That's going to give me 5 millimoles. So now as this reaction takes place, we see that there's more acetate than there is HCl. So we're going to subtract 1 from both of these. So we're going to subtract that. This gives you 0 HCl left over, and that gives you 1 millimole of your acetate. Now, whatever you subtract from over here based off the law of conservation of mass tells you that you're going to add it back to the other side. So that gives you 6 millimoles of your acetic acid solution. So now what we want to do is we want to calculate the concentration of your acid and your conjugate base here. So we're going to do acetic acid first. So we're going to take CH3, CO2H, and we're going to know, we know the 6 millimoles divided by the total volume, which in this case was 10 plus 10 plus 10. So that's 30 mils. So you got 10 plus 10 plus 10. And that'll be the same thing for the acetate in just a second here. So 6 divided by 30 gives me 0.2 molar acetic acid. Now for the acetate ion, we're going to do the same thing. We have to figure out the millimoles, which is 1 millimole. We're going to divide it by 30 milliliters. So 1 divided by 30 gives me 0.033 molar. So we talked about earlier using the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the conjugate base over the acid. We know the concentrations of these two. We just looked at it. We just determined those. Now, remember pKa is the negative log of 1.8 times 10 to the negative 5 plus the log of 0.033 divided by 0.2. So let's calculate this. So I get a pH equal to 3.96, and this is after HCl was added. So what was the pH initially? The initial pH was at 4.35. We know that HCl is a strong acid, and HCl being a strong acid should change the pH quite a bit, but seeing that it goes from 4.35 to 3.96, that's not much of a change. So do we have a good buffer? Yes, we have a good buffer. And again, how do we know that we have a good buffer? Well, we see it from the change in pH has not changed too much, but it's the fact that we have this ratio of conjugate base over acid. And like I said earlier, as long as you have that ratio, you're going to have a buffer. If you're missing one, you can't have a buffer. You have to have both conjugate and its opposite, in this case the acid, present in order to have a good buffer solution. I hope these examples help you out. If you have any questions or anything, just leave them in the comments.